Okay, Unit 7, Day 3, the logarithm. By definition, a logarithm is the inverse of an exponent. So if you want to recall, to find the inverse of a function, we, number one, switch x and y, and number two, solve for y. This is how we've done this before. So let's say y is equal to 5 square root x minus 1 plus 2. We switch our x and y, and we solve for y. We subtract 2 from both sides. We divide by 5. And then we square both sides. And so what we get is we get x minus 2 squared over 25 plus 1 is equal to our y. So this is our inverse function. Remember the notation, and this right over here was our function. Now, our second example is going to be f of x is equal to 2 to the x, which is an exponential function, or y equals to 2 to the x. By definition, what happens is that the inverse of an exponent is a logarithm, and we write that function as y equals to log base 2 of x. So our base here is 2, and our base here is also 2. The 2 is a subscript on your log, so you write whatever the base is as drop down a little bit here. Now to get that, what really happens is this. We switch our x and y, and we use a property that says, essentially, logs are exponents. Because what we get is we get log, or y is equal to log base 2 of x. This I refer to as log property number 1. It is like the number one thing that we're going to be doing for logs. Logs are exponents. And what I mean by that is that you've got this base, and the base, you can kind of figure out what that is. But the y is the exponent on this thing. And that's what the log gives us. If you think of logs or exponents as logs equal exponents, that's what's happening here, is that logs equal the exponent that you're dealing with. So log property number 1, x is equal to 2 to the, or I'm not going to write it like that. A is equal to b to the power of c is equivalent to writing c is equal to log base b of a. Notice that the exponent is up here, and the exponent is here. Logs are exponents. So that's our log property number 1. The other thing that we know about inverses is their graphs. For graphs of inverses, the points are switched. As in, the x becomes the y, and the y becomes the x. So we have spent some time graphing something like y is equal to 2 to the power of x. And what we did to sketch the graph of that is we used our little table of values, and the numbers that we always used were 0, 1, negative 1. We get 2 to the 0, 2 to the 1, 2 to the negative 1. You've got 0, 1 sitting in here. You've got 1, 2. You've got negative 1, 1 half. And that forces us to have this left-hand asymptote line at y equals to 0. So that's what we did the review of our exponential function for. When we want to do the inverse of this thing, and we are graphing y equals to log base 2 of x, the inverse of this thing, notice that all the points are going to be switched. Everything x becomes y, and everything y becomes x. It's going to go through 2, 1 instead of 1, 2. It's going to go through 1, 0 instead of 0, 1. It's going to go through 1 half, negative 1, 1 half, and negative 1 right here. rather than -1 comma a half. And instead of having an asymptote line at y equals to 0, you're going to have an asymptote line at x equals to 0. Now we usually don't write this as a half asymptote line for this one, because remember that a vertical asymptote line is like a brick wall and nothing ever crosses it, so you can write it all the way up. But what's happening is that my graph heads towards that asymptote line and then bends up and over. So this right here demonstrates the difference between exponential growth, which is on the left, and it shoots up, up, up towards the sky really fast, and logarithmic growth on the right, which actually still keeps increasing, but quite slowly. So if I went to another exponential function, we talked about y equals a to the power of x. Remember that base, we decided that it had to be greater than 0 and it can't equal 1, and that's going to be the same for a logarithmic function. So when we do something like this, we use the points 0, 1, and -1. And we ended up with 0, 1, 1, a, -1, 1 over a. That means that when we go to our inverse, which is going to be now y equals to log base a of x as our basic, the table of values that you're going to be doing is different. It's going to be 1 and a and 1 over a, and then 0 and 1 and -1, because our x's and our y's switch. So again, this a value has to be greater than 0, and the a value can't equal 1. So this is now the map for a basic exponential function, which we have reviewed. And this one is now your map for your basic logarithmic function. You need to know them as two separate functions, not as one being the inverse of the other. So I will need to show you how we're going to manage graphing these things. So when we take a look at graphing, we've got something like this. 3 log base 2 of x minus 1 plus 4, so that we can get a good idea. So what we have is we have our main point. And when we take a look at graphing our function by our main point, just like every other function, is going to be at 1, 4, because we think of this as y equals 3f of x minus 1 plus 4. Then we are going to be congruent to y equals 3 log base 2 of x. Now, this is going to be slightly different because I'm going to be showing you your regular table of values. Because we don't know a lot about the log function just yet, we're just looking at the graphs, what we're going to do is we're going to do this. We're going to pretend the 3 isn't there for start. Okay, so we're going to get x, and then we're going to go 1a and 1 over a, and y was 0, 1, and -1. So 1, 0, a, 1, 1 over a, -1. And then we are going to, because this 3 is multiplying our y values, then we're going to do our 3y, which is going to be 0, 3, and -3. Notice that in this case here, our a value is 2. So really, our table of values finally looks like this: 1, 2, and 1/2. 0, 3, and -3, and then we can figure out what happens from our main point. So through our main point, which is going to be at 1, 4, 1, 1, 2, 3, 4, you've got yourself this. There is a vertical asymptote line, just like we had a horizontal asymptote line before. Our vertical asymptote line is at x equals to 1. Then we're going to go from the main point, right 1 up and down 0. So right 1 up and down 0 is going to be my first point right here, which is going to be at 2, 4. I'm going to go right 2, and I'm going to go up 3. From the main point right here, right 2 and up 1, 2, 3, and you've got yourself your graph over here. Right 2 would give us to 3, up 3 would give us to 7. And then here I'm going to go right 1/2, and I'm going to go down 3. So from my main point again, right 1/2, 1, 2, 3, and you've got yourself your logarithmic function that bends up and to the right gradually. My domain for this would be x is greater than 1. My range would be all real numbers, what we're dealing with. So the tricky part is to use this sort of staggered table of values where we're doing our transformation afterwards. So let's try another one. Let's graph something like y equals to negative 2 log base 3 of x plus 1, and then plus 2 or something like that. So my main point to start off with is at negative 1 comma 2. I'm going to be congruent to y equals to negative 2 log base 3 of x. So again, we've got ourselves our sort of gradual table of values. X is going to be 1, 3, and 1/3. So this is the 1, the a, and the 1 over a. The y value would normally be 0, 1, and negative 1, but now we're multiplying our y value by negative 2. So a lot of times you won't even need this center one. You're going to get 0 times negative 2 is 0, 1 times negative 2 is negative 2, negative 1 times negative 2 is positive 2, so you don't really need that. So once we now have our main point, we've got a main point at negative 1 comma 2, so negative 1, 1, 2, so we've got something like that. It's got a vertical asymptote line right through that main point at x equals to negative 1. I go right 1, up 0. So there it is, 0 comma 2. I go right 3 from the main point, right 3, 1, 2, 3 right here. And then I go down 2, 1, 2. So there I am at 2 comma 0. I go right 1/3 from the main point, up 2. I don't usually label that point, just like we didn't with our exponential function, because it's just there to help us with the shape of the graph. The domain for this function is x is greater than negative 1, and the range for this function is all real numbers. Okay, two more things. One more for here. What if I wanted to graph y equals, let's do just log base 2 of 1/2 x minus 1, and then plus 2 or something like that. So my main point would again be 1 comma 2. I'm going to be congruent to y equals to log base 2 of 1/2 x. So what happens here is we have to think about what would normally happen. What would normally happen is that if you had the x, your x values would be 1, 2, and 1/2. But here what we're doing is we are essentially multiplying our x values times x by 2. Divide x by 1/2. So 1/2 x, we're ignoring this guy, and we're getting 2, 4, and 1/2 times 2 is going to be 1. And I would get my y values to be the 0, 1, and negative 1 that I would normally get. So we are doing transformations on these graphs. And once we see our log functions a little bit better, you'll be able to see how the points actually work. So we have a main point at 1 comma 2, vertical asymptote line, x equals to 1. I go right 2 up and down 0. So there I am at 3 comma 2. I go right 4, 1, 2, 3, 4, up 1. So that's going to be at 5 comma 3. And I go right 1, down 1. So I get a graph that looks something like that. You can even label that one if you want to. So again, if the transformation is on the x, do the transformations first. So that's where you're getting your table of values from. Your y values would stay the same because nothing is happening to the y values in this transformation. But we do always start with those basic points that you're dealing with. Domain for this one is x is greater than 1. Your range is going to be all real numbers. Okay, last thing. Remember that when we had y equals e to the power of x, e was our natural growth constant. When you are dealing with y equals log base e of x, which is its inverse, it is used so often and so much that it actually gets its own name. It is referred to as ln of x. And this is called the natural logarithm. And it is essentially just the logarithm base e. The reason why it's abbreviated ln is because the person that it's attributed to is French. And in French, instead of saying natural logarithm, they say the logarithm naturel, and that's where you get your ln from. You will notice that there is a button on your calculator for natural log. There is also a button on your calculator for log, and we will investigate both of those things in the next class. So you're going to be doing some practice and day 3 homework.